This is the first part of the first lesson of Unit 6, Approximating Areas with Riemann Sums. We are going to switch gears here and look at the other side of calculus, which is area under a curve. We're going to get away from rates of change for a while. We'll be back to those later in the year, but we're going to start looking at the other big part of calculus, area under a curve. So if we look at the relationship between the graph of a rate of change function and the area of the region between that derivative graph and the x-axis, we can look at how much accumulation of change has happened. So for our first example, we're going to consider the tropical cyclone Imelda that brought more than 40 inches of rainfall over a 72-hour period in southeast Texas in September of 2019. So, in order to avoid floodwater entering your home, you ran a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. As the storm grew stronger, you got a second pump, and for the next 16 hours, you could remove 900 gallons per hour using 2 pumps. So the first thing we're to do is to draw a graph that models the removal of stormwater from our property and then label the axes correctly. Okay, so here is our graph, and we are going to label the x-axis time, and we're going to make this hours, and the y-axis we're going to label gallons of water removed. Okay, so now let's go ahead and draw our scenario. So for the first 8 hours, we have a steady rate of 500 gallons. So from hour 0 that we start to hour 8, we are removing 500 gallons per hour. Then on the 8th hour, we get a second pump, and our removal is 900. So we're going to start there, and that goes on for 24 hours. Whoops, that went past 24. I thought it was the very last mark. It's the next last one. It's this one. There we go. Okay. So when we say area under a curve, this represents the area between the graph and the horizontal axis. We're to find the area under the graph from 0 to 8 hours. And then what does this value represent in context to the storm Imelda? Okay, so what we want to do here is we want to look at this area right here. We have a nice little rectangle here. And the area of this rectangle is going to be length times width. So our area is going to be, we have a width, I went over wrong, I'm sorry. This, I'm not going to change it right now. This should be over here. I guess I will change it. And this should be here. I don't know if I can just erase that a little bit. I didn't think so. All right. Okay. So this has a width of 8 and a height of 500. So our area is going to be 8 times 500, which is 4,000 gallons of water removed from the property over the first 8 hours. Okay, so next we're supposed to find the total area in the graph for the entire 24-hour period and explain the meaning in context. So we already know that this section is 4,000 gallons. And our next section, we have this part here, this giant rectangle here. So the width of this rectangle is 16 hours wide, and it's 900 gallons tall. gallons per hour. Okay, so putting this together, the entire area is going to be our 4,000 plus, now we have to do 16 times 900, which gives us a total of 4,000 plus 14,400. So we have a total of 18,400 gallons. So in the 24-hour period, a total of 18,400 gallons of water were removed from the property. Okay. Hopefully many of you remember that from last year in pre-calculus. So another way to do it, if we don't have nice areas that we can make shapes of, like rectangles and triangles and trapezoids, we want to use something called Riemann sums. So the idea is to break, I'm going to skip the first paragraph, I'm going right to here, is to break the area down into rectangles, small rectangles that are of equal width, and their height of which is marked by the function itself. So the rectangles end up either being inscribed, which would be below, or circumscribed, which would mean above the graph of the function. And then what we do is if we make them thinner and thinner, and we take the limit of that sum as we make an infinite number of rectangles, they're going to fit perfectly under that curve, and we'll have the exact area. Now that terminology is known as integration. So the things we're going to be specific about as we start this is the idea that f is a non-negative function. That's important, and it's going to be bounded by the x-axis, and we have a defined interval. So just to be sure that non-negative means no portion of the graph is below the x-axis. All right, so there are three different ways we can do this. We can make our rectangles from the touching on the right-hand side of the rectangle to the curve, on the left-hand side of the rectangle to the curve, or the midpoint. So that's what we're going to look at for the rest of this lesson then. So example 2 says, consider a 30-gallon aquarium that is being filled with water at a rate modeled by r of t equals 6 sine pi over at, where t is time in minutes and r of t is gallons per minute. Find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and r of t in height. So you can see in our picture here that each of these rectangles touch the graph in one corner. Now this one's a little off here, but I just think that is the drawing of the rectangle, not really a mistake there, because the rectangles were drawn separately from the graph itself. See, they each touch in one spot, right there, right there. They each touch what is known as the right-hand side of the rectangle. So we're going to go ahead. Each one of these rectangles is 1 unit wide. And so that's going to be one measurement of the rectangle. And the other one's going to be the value when you substitute that x into this function. Now what I like to do is something simple like this. I like to make a table. So there's our t, here's our r of t, and here is our area. And then what I'll do when I'm finished is I will find the total area by adding these up. Okay, so just substituting here, and I will tell you that I used my calculator for this. So when I substituted 1 in, I got 2.2961. write that a little nicer. 2.2961. And these are also going to be the areas, because all of these rectangles are 1 unit wide. The next one is 4.24. You know what? This is not working for me. Let me make this a little wider. Okay. Make this a little wider here. Okay. So this is 4.2426. So 1 times that, we're just getting the same one back. Sometimes your width won't be exactly 1, so you'd have to multiply your R of t times the width. So you'd have another column here for width. So 5.5433. When you put 4 in, you get 6. You put 5 in, you get 5.5433, because we're on the other side of the parabola there. And so our total area, when we add these all up, down, we get 23.6253. So we would say that after 5 minutes, the aquarium holds 23.625 gallons. Okay. All right, so something we want to remember is that by using more rectangles with smaller widths, we can achieve a better approximation. That's why we use the limiting process as we get better at this. In fact, if we consider taking this to the limit of accumulating an infinite number of rectangles, we would arrive at the exact volume in the aquarium after 5 minutes. This is called the definite integral and is represented by this notation. So you have this little squiggly thing. This is the integral symbol. This is the lower bound of your region. This is the upper bound. And we integrate our function over that time with respect to our independent variable. That's why that's there, to tell us what variable are we integrating. Because you guys know from what we did with our derivatives, you can take the derivative with respect to time, with respect to x, with respect to y. So it's important that that's labeled in your integration symbol so you know exactly how you're finding that accumulated area. Okay. So these are the 3 types of Riemann sums that I had spoken of earlier. You can have left-ended or lower sum rectangles, as shown in the first picture. And you see the dots that are all on the left-hand side. And then you can also do it from the right-hand side as well. Or if you want, you can take a midpoint average and have them touch in the middle of the rectangle and not on either end. So I'm going to go over the definition here of the definite integral, and then we're going to continue with some more examples in the next video. So let f of x be continuous on a closed interval a to b, and f of x has to be greater than or equal to 0 for all x in the interval. That's what keeps this above the x-axis. Let interval AB be partitioned into n subintervals of equal length. So that's how we get the width of our rectangle. We take the endpoints, we subtract them, and divide them by the number of subintervals we want. Then the definite integral of f over AB is given by, so the area is equal to the limit as n approaches infinity. This symbol is the summation from k equals 1 to n. That's how many rectangles we're doing. And then what we do is we increase the number of rectangles. So this sum gets larger and larger because n will get larger and larger. And we're adding up these areas. This is the height of each rectangle, and this is the width. And what we find is we end up with our integration from a to b, our definite integral from a to b of f of x dx. Okay, so I'm going to go through how to solve this in the next video, and we're going to go through a couple examples of solving them.